Okay, in this example, we're told we have a reservoir manometer, and we have some vertical tubes. This one has a diameter capital D, which is larger than this one, which has a diameter little d. And when the pressure at this liquid surfaces in both tubes is the same, the liquid levels in each tube are at the same elevation. So when the pressure here is like atmospheric pressure and the pressure here is atmospheric, both are at that level, that equilibrium level line. And then what we do is we apply an additional pressure delta P to the left-hand side, and then that makes the right-hand side move up a distance L. So the left-hand side will go down a distance X when we apply that delta P. The right-hand side will go up a distance L. And the pressure in the right-hand side is still P atmosphere. And what we're asked to do is develop an algebraic expression for the liquid deflection in the small tube in terms of this additional pressure delta P and some of the geometry. Okay, so this will be a matter of analyzing this manometer using hydrostatic pressure relations. So let's go ahead and work our way around. We'll find the pressure at this point. Let me just call this point 2 in terms of starting with the pressure at 1. So pressure at 2 will be P atmosphere, and then starting at the pressure at 1 we'll have P atmosphere plus delta P. Then we're going to move down this distance. We're going to move down all the way to the bottom here, and then go horizontally, and then come back up to this point. So by doing that, what we're doing is we're adding in the weight of the fluid here, but then we're going to subtract it back out so that we'll have no net change in pressure. So the pressure right here at that location is still P atmosphere plus delta P. It'll be the same pressure that we have over here because we're at the same elevation. Now we're going to move up this additional distance, which is a distance of X plus L. So we're going to be removing some weight there to move upwards. So we're moving upward again a distance of X plus L to get to this point. And then that will be the pressure at 2, which is P atmosphere. And it's a negative because we're moving upwards. We're removing some weight. We don't have to have as large of a pressure because we've removed some weight. All right, so now we can go ahead and simplify this relation a little bit. You see the P atmospheres drop out. And then we'll have X plus L is equal to delta P over rho G. So unfortunately, we don't know what X is just yet. We need to figure out what that is. And the way we can do that is just by noting that we're conserving volume. When we move down here, we're pushing down a volume of fluid of X times the cross-sectional area here, which is pi capital D squared over 4, and then that additional volume gets lifted up on this side. So when we conserve volume, let me just make a note of that, conserve volume. It's an incompressible fluid, so we're really just conserving mass. But the volume that we push down on the left-hand side is pi d squared over 4 times x. And then the volume that moves upward on the right-hand side is the L times pi little d squared over 4. So again, we're pushing this volume down, and then that volume, it has to go up by the same volume over on the right-hand side, so it's going up by a distance L. So we can go ahead and solve for x in terms of L. So it'll look like that, and then we can take that and substitute it in right up here. So let's do that. So then we'll get L, 1 plus little d over capital D squared is equal to delta P over rho G, and then we'll do one last little bit of algebra. And that's our final answer. So just to kind of recap how we went about solving this problem, what we did is we did a manometer analysis. So starting at this point, point 1, we worked our way around the manometer to get to point 2, so that's what this line is. And then we had this quantity x that we didn't know, and to find that, what we did is we conserved volume. That we're assuming that the liquid is incompressible, so it's just like conserving mass. So the volume that we push down here from that dashed line will be pi d squared times x, capital D. And then that by conserving volume, that's the same volume that would move up here, which would be pi little d squared over 4 times L. So that's how we got to this point, and then after that it's just algebra. Okay, we'll go ahead and end it there.